there, physicists. Welcome back. So hopefully you worked through the basic circuit notes, and this is the second piece, which is talking about circuits with multiple resistors. So the second part of the FET simulation stuff that you did also involved um, multiple resistors. So we're just going to kind of put it all together and make sure that it makes sense kind of in a notes perspective. Again, this notes sheet is available up on Canvas. So if you haven't yet printed it or accessed it, you're very welcome to do that as we get started. Okay, so there are lots and lots and lots of ways to do complex circuits with multiple batteries and multiple um, bulbs and multiple resistors and all kinds of lots of complicated things. But generally, if you look at a really big, scary circuit, you can boil it down to pieces that come from two different types of a little bit more complicated circuits. The first one is called series, and a series circuit is just a circuit. We're just going to keep it simple here with just two bulbs. Involves a battery. Remember we said last time that a battery looks like this, okay? And then we've got some wires, and then we've got multiple bulbs. We're going to do two of them. So I'm going to actually go like this. And one thing to know is that wherever you put the bulbs on or the resistors on a circuit, it doesn't really matter. So I'm going to put one here, and then I'm going to put one here. And the key to a series circuit is that there is only one path around the circuit, okay? The other type of circuit that, we can kind of distill it down into two different types. The other kind is called parallel. And unlike a series circuit where there's one path, in a parallel circuit, there are multiple paths. So I'm going to go ahead and draw my battery again, okay? And I'm going to draw one path that those electrons might go through. So there's a path. And electrons might just go through that path right there, or they might take this path over here through a different bulb, okay? Now, in this one, so we're going to say we have multiple paths, and those paths may be identical and they might be different. So we might have different bulbs, we might have the same, or resistors, same kind of deal. But for our situation, I'm going to just make a little note down here. For our situation, we are going to say that all of the bulbs are identical. And again, we're just kind of keeping it simple in this lesson. So when you do this in a more advanced way, just know that that's not always true. But for us, we're going to say that they're all identical. One other thing to note that's really important to know, because I know that sometimes it gets confusing for people when they're just starting out with circuits, is that the length of the wire doesn't matter. So often students want to say that an electron is much less likely to go around this path than it would be to go around this path because it has to go farther. And actually, for an electron or for a charge, the length of the path does not at all matter. Okay, it's kind of path blind. So just know that in this case, both of those paths are equally likely. Okay, now as we look at what's going on in series and parallel circuits, in addition to Ohm's law, we have two other rules that kind of dictate everything that we do. So the first rule that we have is called the loop rule. Okay, that's rule number one. And basically, the loop rule is just a statement of conservation of energy. Okay. The loop rule says that all of the energy that an electron has must be dissipated By dissipated, I mean given off or lost, right, around one complete loop. So by that I mean if an electron has 9 volts of energy, if it's connected to a 9-volt battery, when it goes all the way around one loop, it will lose all of that energy as it goes around the loop. Okay. And we know also the other little piece of this is that each electron only follows one loop per trip. So we haven't gotten into a lot of the details, but if we think about the water analogy that we had in the other video, if we lift that water up or we lift those electrons up, we give them some energy, they're going to fall, right? That water is going to fall. And if we think about kind of how that works here, we'll say that the water falls or the electrons fall, they lose energy going around this loop. That seems to make pretty decent sense. In a parallel circuit, there are lots of different ways it can go. So we're going to start at the positive, and it's going to fall either this way or it's going to fall this way. Okay. But the point that I'm trying to make with that loop rule is that it would not do this. So this is not an option. It's not going to go up, go through here, and then go back this way because that would be going against the path, right? The path is saying go down. And so it's only going to go from the positive, that's the long side, to the negative, the short side. It's not going to go backwards, right? Oops, kind of lose some of my circuit there. Okay, so it's just an important thing to know. Okay, so that's the loop rule. So what do we do with that, Miss Kay? Well, let me tell you what we do with that. Let's talk about it. So we're going to apply this situation, this loop rule, to each of our circuits. One other little note that just to kind of make our life clear while we're doing these examples, we're going to suppose that the battery has a voltage of 9 volts in both cases, right, in both the series and the parallel situations. And we're going to say that the bulbs are identical and that they have an operating resistance of 10 ohms, just to keep things simple. Okay. Now, there are caveats with all of this, but we're just kind of keeping it simple. So we'll just leave it right there. Okay. So let's apply the loop rule to our series circuit. That's the first one we've got here. So in this case, it says all of the energy must be dissipated around one complete loop. So that means that if we've got 9 volts, our 9-volt battery provides energy per charge of 9 volts to all those electrons. Okay. It's got to drop 9 volts around the loop. By drop, I mean dissipate, get rid of. It needs to lose that 9 volts somewhere around the loop. Where's it going to do that? Well, in general, the wires are not going to dissipate any energy, right? We said that the length of the wire doesn't matter. The resistance of copper wire is very, very, very low compared to anything else on the load. So, unless we don't have any resistors or bulbs, the wire is negligible. So that means that 9-volt drop has to happen only at the light bulbs. Well, if there are 2 light bulbs, that means that there's going to be a 4.5-volt drop at each bulb. And that's because they're identical. Again, it can get more complicated if you start using different kinds of bulbs or different kinds of resistors, but we're going to keep it simple here. Okay, so there's a 4.5 drop per bulb. In that case, well, yeah, let's hold on to that for a second. Let's go over to our series, or excuse me, our parallel circuit. In this case, we have a 9-volt drop around the loop as well, right? Oops, that looks kind of yucky. Let's fix that. Okay. But electrons are only going to go through one bulb or the other. Remember, we said that each electron only follows one loop per trip. So that means that in each trip that it goes through, there's going to be a 9-volt drop at each bulb. So again, each electron in a parallel circuit is only going to go through one bulb. So it will drop all of its energy. It will lose all of its energy. By lose, I mean dissipate. It's going to give it off as heat or light um, just one time. So it's got to lose all of it there. So what does that mean for the numbers? Well, I'm going to go back to the series circuit here for a minute, and let's figure out what the current is going to look like. So I, remember, is equal to V over R. And if we're talking about just one bulb, well, the voltage across that bulb is 4.5 volts. We said that's the voltage drop across one bulb. We said the resistance is 10 ohms. And so I can even do that one in my head. Convenient numbers for me to choose there, right? 0.45 amps. So that's the current through that bulb. All right, well, let's take a look at this situation over here. In one bulb with a parallel circuit, I've got I is equal to V over R. My voltage now across each bulb is 9 volts, so it's a higher voltage, okay? I've got my 10 ohm resistor, right? That's what the bulbs are. And so I've got 0.9 amps of current going through each of those bulbs. Okay, and that's again through one bulb. We'll get to the next part in just a second here. Okay, so you can see from that right there that each bulb has a very different current. Current is very closely related for a bulb to brightness. So in this case, the bulb in a parallel circuit is going to be brighter. We're going to kind of see what that all looks like here in just a second. So that's circuit rule number 1. Let's do circuit rule number 2. So circuit rule number 2 is called the junction rule. Also affectionately named what goes in must come out. Or for a more technical term, a more maybe scientifically minded term, we can describe this as conservation of charge. And basically what the junction rule says is that the total current, that's the flow of charge, okay, at the start and end of a circuit must be the same. Okay. We can also say that any split in current must be the sum of the total current. And we'll talk about what that means in just a second. Okay, so I feel like I'm kind of losing track here because my paper is so big. So we're going to start again with the series circuit. Let's take a look at the series circuit. We said early on that for the series circuit, there is only one path. So there's not really any coming in or going out except at the beginning and the end. That means, so I'm going to go ahead and write that down here, that there's only one path. That means there are no splits, there are no junctions, okay? That means that in a series circuit, the current must be the same throughout the circuit because we can't add any or lose any, and it's just got to be a flow, right? Any charge that goes in has to come out. So there we go, okay? In the case of our parallel circuit, that's not quite the same, not quite the same deal because there are multiple paths. So let's take a look and see what happens with the junction rule. for a parallel circuit. So we've got multiple paths. Okay. That means that the total current is the sum of the current through each bulb. Okay. So then if we apply this to the whole system with our numbers that we just used, okay, we knew that we had a current in the series circuit of 0.45 amps, and that means that the current everywhere, the total current or the overall current is 0.45 amps. In the case of the series circuit, we had zero point 0.9 amps going through each of these um, bulbs. So there was zero point 0.9 amps going through here, zero point 0.9 amps going through here. Well, if we're going to add those together, again, what goes in must come out. That means that there must have been a total current, remember that's charge per time, a total current of 0 0.9 going through one of the bulbs and 0 0.9 going through the other bulb, which gives you a total current of 1.8 amps. So there's decidedly more current going through that parallel circuit than there is through the series circuit. Okay, more current means brighter bulbs. Less current means dimmer bulbs. All right, I'm going to make a third video here with the ranking tasks, mostly because my kids just woke up. If you have any questions, of course, throughout all of this, you just let me know. Hope all is well.